If you look at a steel bridge, you probably see a rigid, unmoving skeleton. But you've been lied to. At a microscopic level, that solid steel is actually a giant, incredibly stiff spring. When engineers test standard mild steel, they map this on a stress-strain curve. As you start pulling, the stress shoots up in a perfectly straight line. That steep slope is its stiffness, the modulus of elasticity, a massive 200 gigapascals. This entire straight section is the elastic zone. Up to an exact point called the proportional limit, the metal obeys Hooke's law. If you let go, it snaps perfectly back to its original shape, just like a rubber band. Push mild steel past its elastic limit, and it does something bizarre. The stress spikes to an upper yield point, then suddenly drops. Then it enters the yield plateau. The stress locks at 250 megapascals, but the metal just keeps stretching like taffy. Instead of snapping, the steel yields. On an internal level, entire planes of atoms are sliding past one another along slip bands. The material is permanently deforming, absorbing the energy rather than breaking. You would think once steel stretches out of shape, it's doomed, but it actually fights back. After that flat yield plateau, the steel enters a phase called strain hardening. It sweeps upward, taking on massive loads until it peaks around 550 megapascals. We call this absolute limit the ultimate tensile strength. So how does stretching it make it stronger? Inside the steel, microscopic sliding defects called dislocations are moving around. As you pull harder, they crash into each other and tangle up like a brutal traffic jam, locking the metal rigid until it simply cannot take anymore.